Right. This week we're moving into sheet metal. You've done some of the developments using sheet metal templates, but we really didn't get into how to create things with sheet metal tools. So that's what we're going to do this week. Um, the patterns and developments you've been working on have basically been a zero thickness. We've just been doing the patterns. This week you'll be doing bend radius calculations. And anytime that you bend metal, it causes it to lengthen or creep, if you will. And so you have to take into account the amount that that metal is going to stretch. And that's why we do the bend radius calculations so that our finished product is the correct size. Now, with a lot of a lot of these shapes, you could make it in Inventor just doing normal sketches and extrusions. The problem is it would not be accurate when you laid it out in a flat pattern because you have to take into account the creep or the increase in the size of the metal when you do a bend on it. Now, when we say sheet metal, most of the time we're talking about most of the time what people think about is ductwork, heating and air conditioning ductwork, and the various parts that go together, just like you did the last couple of weeks um, that triangulation lab project that you worked on. That was an air handling system. Well, now we're going to be doing some stuff in Inventor, and you need to know about bend radius. And then the things like the K factor, um, a lot of the stuff is based on the type of metal, the thickness of the metal, and then also the machinery that is going to be used to create the bends and the folds. Because every piece of equipment that does the bendings may have a little variation in how it works. So those are the kind of things that you would learn in your job based on where you're working at and how the equipment affects those things. And it's not just ductwork, it's anything that can be formed of metal. Some of you may have seen joist hangers and hurricane ties. Um, a lot of lots of things are formed. A real common one is dumpsters, garbage dumpsters. If you get a chance to look at them sometimes, you'll see a lot of the metal components of a garbage dumpster has been bent and formed. It's the same principles. And then also cardboard boxes, cardboard packaging. It's the same principles, just different values and materials. Okay, so here's one that we're going to work through on this tutorial, and it'll have some of the tools that you're going to use. So I'm going to, and this is the drawing. Now, when you create your pattern, you're creating you're going to create it into the 3D shape, okay? And because these are the critical dimensions that you need is what's the finished size and shape of the thing. But then when it goes to manufacture, you need what's known as a flat pattern. And Inventor will unfold your shape, taking into account the bend radius, the material thickness, and the amount of creep in the metal from those bends. And this is what the manufacturer needs in order to make that shape. Okay. All right. So we're going to start off with, this is going to be a metric one, but you would start by setting your project. I'm just going to leave mine in default. But you would create a project for the assignment. For the tutorial here, you can leave it as default and save it somewhere. So we're going to go with a new metric sheet metal millimeter part. And then pretty much the first thing, you should have the sheet metal tab right here. It should be showing up as part of this template. And we want to set up our sheet metal defaults. Okay, and this is how the program is going to affect things. And wherever you're working, like I said, they're going to have the defaults that they want to use. Okay, so for our sheet metal rule, we're going to use the default millimeter. These can be edited um, to to create whatever you want from it. In this particular case, we're going to uncheck thickness from rule, and we want to set our thickness to 1.17 millimeter. That's the thickness of our material that we're going to be working with. And for our material, we're going to change that to stainless steel because different types of metals react differently to being bent. The unfold rule, we're going to leave that as the default K factor. So we'll say OK here. Now let's start a 2D sketch on the XY plane. And one of the things it gets a little confusing when you're drawing this, when you're building your shape, because when you create your flat pattern, that is the inside of the part, and everything should fold up from the flat pattern for the most part. But we're going to start on the front, and when we get done with this, it's going to be reversed in 3D. But we're going to work on this one here. So we're going to start here. Let's start with our line at the origin, and we're going to go off to the right 62.5 millimeters. And then we want to go vertical 18.5 millimeters. We're just going to come horizontal, go vertical again, come back over to the snap over the origin, and then down to close that off. Okay, and so we should have perpendicular constraints at all the corners. So now we're going to apply a dimension over here on this side of 32.5, dimension of this line here of 46.5. Okay, and our sketch is fully constrained. And so now we're just going to finish. Okay, so we've got a sketch that has no thickness, just like you've been doing in AutoCAD. Okay, except for we have no bends on this one here. We're going to start that. Now, in the way that the sheet metal tools work is the first thing that you create is known as a face. And that is going to be our base that we're going to work from. And everything after that, after this first face that attaches to an edge that's coincident to it, a bend will be created from there. And what I'm talking about, let me come back over here. So this is my base face right here. This was another face that was created coming out, and the program creates the bend that goes with it. And the notches that you see here, like this right here, anytime you bend the metal, if you don't have a notch of the appropriate size, when you do this bend, it will tear that metal. Okay, so the notches are built into the program so that it creates it based on the default rules that we have set up. So you don't have to worry about notches for any of the projects that we're working on right now. All right, so we're going to come up here and we're going to go face, and it should automatically select that sketch. Our sheet metal rule should be default, and we want the direction to be forward, coming towards us right here. And that you could name it if you want to. Solid 1 is fine. That's what it's going to put over in your browser tree. And so we'll say OK. Okay, so here we've extruded our part, or we've created the face, and we're going to start with a flange. And a flange will create another face, well, in our case, perpendicular at whatever angle. but it will create the bend automatically from the point that we started. And in this one, we're going to go with the bottom edge right here. And you can see how it created our face and our bend. In this particular case, we want to change direction. So we'll come right here and change direction. And we want the distance to be 13.57. Okay, and so now that I've got it in here, I want to show you some of these options. And as you work through the bend radius calculations, you'll see that however the part is dimensioned, from what face it's dimensioned, whether it's the outside face, the inside face, the radius point, or maybe it's the point of intersection of the planes, however it dimensions, that's the options that we choose here. And so in this particular case, we're using from intersection of the two outer faces. Okay, I could go from the intersection of the two inner faces, and you see that changed where my dimension came into play from. Another option is from the actual selected edge, which I chose the bottom edge here. Or it could be from the tangent plane. And these last two change based on your angle that you're working from. So let's go back to the first option there. And in the angle placement, since we got a 90-degree angle, it doesn't change that much, just like up above. Okay, some of the options. But if I were, let's say, let's change this to a 45-degree angle. And now if we change some of our options here, you can see how that changed the placement of our whole face and the bend that we had. Okay. So let's go back to normal and let's take that back to 90. Okay. And so that's some of these options that you've got going here. Now, we don't want this to be the up here, the edge. This is a full width edge. And if you need that, that's what you would use. In this case, we want to define the width that we want our part to be, and we want it to be 18 millimeters. And if you just leave it as that, it will center it in whatever you chose as your edge to start with. We don't want it centered, we want it offset. And so you click the offset button right here, and you have to select what face you want to measure from and the distance. And so I want to offset it from this face here, a distance of 21.5 millimeters. And so that from this face of the flange to this face of the base will be 21.5 millimeters. And so now I'm going to say OK, and that created it. All right, so now we're going to create another flange, but this time coming up. So we'll go flange. I want to choose the bottom edge right here. I want to make sure it comes up, so it's flipping up. A distance of 7.5 millimeters. And I want it centered, so I'm going to go a width of 11 millimeters. And so that's what we should look like there. And we'll say OK. So that's got the bottom edge of what we're building. So now we're going to come work on the top. And okay, I'm just looking at my notes. So we're going to go flange. My notes say inside edge, but I'm not too sure about that. I'll go ahead and pick the inside edge. Distance 13.57. Set my width to 20.5, and let's do an offset from this face of 20.5. And I'm going to say OK. I believe I've got that. We'll say OK. I may have to come back and edit that. We'll go with that. OK. Now we're going to do another flange coming down. So we'll go flange. We're going to choose this top edge here. We want it to come down. A distance of 8 millimeters. We want a width of 8 millimeters and an offset from this face of 9.5. And we'll tell that OK. All right, and so that's got our downward facing edge. Yeah, I can see right. Well, let's see. No, those line up. Okay. So now we're going to create another flange, but this one will have a 0 angle to it. So I'm going to choose the top edge here. And let's change our angle to 0 degrees, which will make it come straight out. We want a distance of 3 millimeters, a width of 5, and an offset. We're going to say 0, but we want the offset face to be from here. But we need to change direction. That was weird. Huh. I'm going to cancel that and start that over because that should have started it right out. So let's go again. Flange, top edge. Distance of 3. Zero degrees. Width of 5. And an offset of 0. That's weird. Really weird. Okay, so let's go with a 5. Whoop. Oh, I see. My bad. This 2025 version I missed it. The little button right there, flip direction. Okay, and so that's how that should work. So we'll say okay. All right, and so there's our part. If we look at it from a side view, you can see everything's lined up there. These are lined up coming down. Just take a look around at it, make sure you've got what you look. And so I'm going to go ahead and save this now. As we've got going. Now with a regular part file, you would, for cuts, you pretty much would do sketches and extrusions. With sheet metal, you want to use a cut command. And you want to use hole commands because this tells the program that you're working in sheet metal and it needs to take into account various things that are complicated for me to explain. So we're going to do, and this works out really well because you could make your overall part, and if you have an assembly, like say this is actually a mount for a motor that goes inside a larger assembly. And so there's several holes that would go into it. You could actually put your part in your assembly and then project geometry from the gears, the axles, or the screws or whatever onto this to create the holes in it. But we're just going to go with it here. So we're going to start a 2D sketch on the inside. And let's draw a circle just somewhere right up in here. Placement is not that critical, but let's make it 9.5 millimeter diameter. Okay, and let's finish our sketch. And let's use the cut command right here. If it doesn't select your sketch, go ahead and select it. And right here, distance, you could put in your distance, you could do through all, or we could just choose the option for thickness. And it knows that it has to go through the thickness of the part. Okay. Now, holes pretty much work the same way as they do in regular Inventor. So let's do a sketch on here, and let's put a point. You could draw a circle, or you can do a point. Let's put it right there. And then let's do a hole. And these, you've used the hole tool before, so you know pretty much all the options. All of these will work in the sheet metal. We're just going to do a simple hole through hole. We want it to go through all. And let's set it at 3 millimeters diameter. That'd be fine. And we'll go OK. And now let's put in a couple of tapped holes. Oh, sorry. So I'm going to pop another sketch over here. And I want to put 2 points here. And I want them to be constrained horizontally with each other there so they line up. And of course, you would dimension these as you're doing your part. I'm not too worried about it in the tutorial, but you would dimension these points. And so now let's go hole. And let's go with a tapped hole. For the type, you want to choose whatever type screw you're going to use. This is a metric part, so we're going to use metric screws. Let's go with a 2.5 millimeter diameter. Okay. We have options of a fine thread or a coarse thread. And with metric screws, the first number is the diameter. The second number is the pitch or the distance between the threads. So we've got either a 0.45 or a 0.35. We'll leave it at 0.45. The class is the tightness of the fit, and that's pretty much standard for metric threads. Let's see. Yes, we want to go full depth on it. For termination, we could tell it distance, or we could just tell it through all. That would be fine, but I want to show you here. If I were to go with a termination, this is how deep you want your hole to go. And this works in other places too, not just right here. Anytime you've got a measurement with a pull down next to it, you can come here, and it has the last few used dimensions that you've got there. Or you could go list parameters, and you've got all these things that are available to you in the part. And in our case, we can choose thickness and then tell it OK. And so that put tapped holes in those two places. Now we have a corner round and a corner chamfer tool here that works very much like the fillet and the chamfer tool, but because it's sheet metal, it works a little differently. So let's go with our corner round tool, and let's set our radius at 1 millimeter. And then we want to select the 5 outside corners of our part. Just like that. and we'll tell it OK. Um, oh, look, I'm going to show you one other thing in there. Let me go back in. Okay, so if I do right here corner, it's individual picks. If I do feature, it will pick every corner. Um, Let me just delete those and start over. Corner round 1 millimeter. If I go feature and pick the base, it picks every corner, but it picked the inside corner right here also, and that's not what I want. So I'm going to cancel that and start that over. Corner, so I'll go through and pick those. You may have already known that, you may not have, I don't know, but we covered that. And so we'll say OK. Okay, so now we've got a finished part. So I'm going to save it. There are other tools here. Hems, and the hem is like a treatment for the edge to fold it over. Lofted flange, we've done that with our patterns and developments that we kind of worked on. Bends, you could draw two faces and then use a bend tool to create a bend between them. Okay, so there's several other tools here that you can use. Um, any time that we're going to use like the punch tool in particular is you have to set what's known as an A side. Okay, so that the machine knows how to dimension those things. And typically this is how it's going to unfold. If you don't pick an A side and you just go to create flat pattern, it picks an A side for you automatically. But when we create a flat pattern, it jumps back to the front view of what we had. And if you will remember, this was the orientation that our part was in as we built it, because this part right here folded in towards us and this folded down. And so this is the orientation that we would use when we place it on a drawing, because this is the flat pattern, the inside of the pattern. Okay, and so when you're in flat pattern mode, you can't save your project or you can't save your file. You have to come back over to your folded model, which would be right here. Go back to folded model. Okay, now you can save your file. Now let's go back to our flat pattern. You got this right here, bend order annotation. And so it should automatically, it did it in the way in which we built this thing. Well, no, it didn't, because we built, well, anyway, it numbers the order in which they go. You can do those manually. You can take whichever it is. Okay. So I'm going to pause the video now. Oh, see, yeah, I tried to save it in flat mode. I'm going to save my part, pause the video, and we'll start another one on preparing the drawings.